So, welcome to my channel. Today we're going to discuss about understanding bacterial cell wall, and my goal here is to just give you the basic information on how do bacteria developed their cell wall and why do we use antibiotics to kill the bacteria, right? And where are all these antibiotics go? To just kind of where do they go to kill that bacteria? So that is what we're going to learn today, and my goal here too is just to give you an idea on antibiotic stewardship, right? As we all know that a lot of the hospital nowadays, they want us to participate with the usage of antibiotics. So they want us to be an advocate for, do we really need to do that? Things like that. Okay. So as you may know, for those who are new in nursing, what is bacteria? How does bacteria look like? Right? Sometimes you get a phone call from the lab. They said, "Hey, Manny, I'm gonna give you lab result for your blood culture," and then they would say gram-positive cocci on 2 clusters, or gram-negative cocci. When I was new, I don't even know what they're talking about. I just said, okay. And then I tell the doctor, right? But then I realized over the years that I've been an ICU nurse that it's not right if I don't know anything, so that um, just be a passive nurse and be codependent with a doctor. It's not really empowering, right? So that's when I realized that I really need to understand. So that was about 30 years now. Because when you're new, you don't know anything. And then I end up like reviewing my notes way back in college. And then that's when I realized that, oh, yeah, we discussed this, but it wasn't, I just didn't retain the information. So since then, I was able to just reviewing it again until I became a nurse educator after 25 years at the bedside. That's when I'm starting to sharing it to the new nurses or to the staff nurses. So that's my goal today, is to just give you guys an idea what is bacterial wall synthesis, right? How do they develop their wall? Just like the Great Wall of China. Are you not interested to find out how did they build that too, right? So many, many years ago. Okay, so I just want you guys to give you an idea that when you think about bacteria, they have a cell wall. They have a, like a house, so to speak, so that nobody can ever destroy them or invade them that quick. Okay, so when they say about bacteria, there are a lot of shapes, and I just want to give you an idea. When you hear that cocci or cocci, right? Cocci, cocci, there are diploci or diplococci. There is a staphylococcus. So when they said staphylococcus, right, like Staphylococcus aureus, those are cluster. They're here like this. And then streptococci, they are formed like this. So just to give you an idea, what belongs to the cocci family? Staphylococcus aureus, your MRSA. Streptococcus pneumonia, your Neisseria gonorrhea, right? What about the E. coli? So the bacilli or the bacillus is also a bacteria, although the shape is more long, and E. coli, salmonella, those kind of things. So there is also a diplobacilli, that's two, and then there's a streptobacilli, right? So that's like elongated one. And then the spirochete, the typical one is your Treponema pallidum. So although you don't see this because you're not working in the lab, but I just want to give you an idea, because as a nurse, we give health teaching, right? So one time, I was a nurse educator already at that time, and I was just listening to family member conversation, and I heard a young girl came in to visit her grandmother, but because she is in the nursing school, well, I shouldn't be calling her a young girl. Um, and she was asking the nurse about, I think it was one of her assignments, and why does the blood doesn't clot, right? So at the back of my mind, I already know the answer because hey, I learned that in school, but not everybody is in the same page. So the nurse wasn't answering because she wasn't so sure what to tell her, but then she just said, I'm gonna come back and I'm gonna tell you why, right? So the nurse came out of the room and then ask me because I'm her educator. So I end up like explaining it to her like the endothelial cell. There's a lot of enzymes in there that will really prevent the blood from clotting. However, if you destroy your endothelial cell, that's when But it didn't really. It wasn't an instant answer from the nurse, and so, to me, what would they think about us if we cannot answer it right away, right? So that's what I call we should be ready to just give that, quick answer, um, go direct to the point, and then go from there. So same way here. I just want you guys to understand how that bacteria form, right? It's very basic. And I know some of us actually had those before you became a nurse or got into the nursing program. You have your prerequisite like your microbiology. My nursing is it's part of that 4 years. We have a microbiology on our first and second year. That's why the pathophysiology is really important in nursing so that you can understand, right, the disease process. So that's my goal, is to just refresh review with you again what is going on here. Okay, so again, it's not for you to see, but at least to know. So cocci are round, the bacilli are long, like a oblong, oval shape, but it's long. And then your spirochete are like the like a rope or something. Like this is the shape. All right. So why and what is the function of bacterial cell wall? Why is it so important for the bacteria? I think it's the same question. Why did the Chinese build the Great Wall of China, right? Because I remembered learning that from the world history. It's just um, to just like to protect them from the invaders. So at least it wouldn't be easy for the invaders to, or for the enemy to cross, right? If there's a wall, it will take a lot of time and effort to penetrate that. I think it's the same way here. So it gives shapes to the bacterial wall and prevent osmotic bursts. Why? Because when the bacteria, and I will tell you how the bacteria form or how do they develop their wall. So it's just a simple sugar, like we call it the sugar backbone, right? So when the bacteria is getting mature, they become the increase of osmosis, right? And when there is that osmotic pressure inside, they will, um, absorb more water. And when they absorb more water, then they will swell, and if they don't have a wall, they will burst, right? So pretty much they want to have that cell wall to prevent them from bursting and also from getting killed, okay, if that makes sense. But this is what I was saying, that sugar backbone, or we call it glycans, and there is this what we call the peptide links, and we're going to review that. But one thing that I want you guys to understand too is when you hear mycoplasma, mycoplasma doesn't have any cell wall. So if they don't have any cell wall, then they don't have a shape, right? So mycoplasma. You have to remember that the bacterial cytoplasmic membrane, that's where the, like, the cell, if I may use that word, has a double layer with phospholipids, right? So let's assume that these are your backbone already outside, but how do they come out outside the cell, right, or the membrane? So it starts by having this simple sugar. We call it the NAM and the NAG. So NAM, NAM, NAM stands for N-acetyl-muramic acid, right? And then the NAG is N-acetyl-glucosamine, glucosamine. So pretty much they're just simple sugar. So there is a monosaccharides that will actually activate the NAM and the NAG, right? And when you activate them, there will be what we call the peptide. So there is a peptide link, and then it requires a uridine diphosphate, and that will trigger the more protein binding, right? So you have those proteins developed in there, and this is what we call the amino acids, right? And when they have all these processes, we call it polymerize, right? You make them really unite together. They will bind together. A part of that cytoplasmic membrane, there is what we call the bactoprenol phosphate, or the BPP, bactoprenol phosphate. So what does it do? That is a transporter, right? It was just built to, like, hold onto the NAM and the NAG and the peptide, removing the uridine diphosphate. What does it do is it will transport it outside. So from taking it from the inside to the outside. So that is what's gonna happen. Okay. So there you go. So now that the sugar backbone now is now outside the membrane, the cytoplasmic membrane. So now they will be surrounding that cell with a lot of these sugar backbones. We call them glycans, right? So you have to remember of bactoprenol phosphate, because it's really important to understand his role, okay? And you also have to remember that this formation of the amino acid, it's really important because, in order for us to kill the bacteria from not forming their wall, you have to stop that from happening, right? That peptide formation of the amino acids, okay? Um, And then there is another enzyme that I want you guys to understand, and we call this as our glycosylation. What does it do is it will stick those NAM and NAG. They will stick them together, like, you're cementing them to each other so that they can form a line, right? So that is what we call glycosylation. It's a process of putting them together. And there is another enzymes inside the cytoplasmic membrane that is responsible for joining the peptides together. We call it the peptide link, peptide chain, or peptide links, right? So when you are now putting this together, it will solidify, become really a very good, what we call sugar backbone. So that process is called transpeptidation. Okay, so we use that term glycosylation. It's when you are putting them all together, and then transpeptidation when you're connecting their nose. Well, they're not really nose, but they're peptides together to form like a web like this. Okay. So those are really important elements and concept to understand so that when we are talking about antibiotics, you know where they're going to either fight or go directly to that area to kill it. Okay, so there is what we call the autolysin. This autolysin, it's actually built as part of the membrane to make sure that he is responsible in helping out in reshaping, right? So what does it do is it will cut the membrane or the cell wherever it changes the form or shape, right? However, inside there, the bacteria said, I'm watching you. You cannot be so naughty, okay? So I'm watching you all the time. I am watching you all the time. So who's watching him all the time is what we call the autolysin inhibitor, right? So that autolysin inhibitor is the guard of this bacteria, while they're creating their wall. He is watching autolysin so that he won't destroy the wall, right? However, when you think about him, he is on our side. We needed him, right? So we are now watching the autolysin inhibitor and we will go for him. So also it's another concept that you need to understand. Okay, this is what I was referring to, like how those molecules, in terms of like your microbiology. I'm just giving you guys an idea how does it looks like. So there is that cross-linking in here. This is what I was telling you, the amino acid, the L-alanine, glutamine, lysine, and the alanine that putting those peptides together so that they can form a nose, right? If I may use that term. Bacterial wall have that long glycan unit with peptide chain. So it's just one, but it's just continuously forming and connecting to each other. So they call that peptidoglycan. So another concept I want you to remember, because when we're talking about gram-positive cocci, like GPC, that when you get a phone call, they said, hey, Manny, your blood culture is gram-positive cocci. What does it mean? It's just the number of peptidoglycan, okay? Like how many layers of peptidoglycan. That's just it. When it's gram-negative cocci, there's only a thin, not thick, very thin peptidoglycan, but they have another outer ring, right? So in the middle is peptidoglycan, and outside is another, we call it another. Let's go back. So this is your NAM, your acetylmuramic acid, and this is your NAG, your glucosamine, and I told you about the peptide. So this is how it forms. And we talked about this already, right? Your glycosylation and your transpeptidation. There you go. And this is how they look like. Okay? All right. So the amount of peptidoglycan, outer membrane. Okay, that's the word that I am actually looking. So this is your gram-negative cocci. Look at your peptidoglycan. There's only like very thin, but there is an outer membrane, like what we call it porins, right? So the porins, that's the difference between the two. Gram-positive cocci is your peptidoglycan is thicker, and your gram-negative cocci is thinner, but you have an outer membrane. So what is the implication for us as nurses when you think about your gram-positive cocci? Sometimes there is what we call the beta lactamase. So the beta-lactamase is the it comes from the bacteria. It's like a cutter that he will release out there into the peptidoglycan to cut the penicillin if you're giving them penicillin. So that's what we call beta lactamases penicillinases, right? Because no matter what you do, if that beta lactamases cut the penicillin will disconnect. It won't go to that what we call the penicillin binding protein, right? So they need to go there because that's their target, right? I need to get there to that penicillin binding protein so that I can destroy the wall. However, the bacteria is very smart. They created their own army. So there is that beta lactamases. They will go out to the peptidoglycan, right? Let me go back here. So like this one is Staphylococcus aureus. They will go to that peptidoglycan, and then they can even go into the circulation. Okay, so when they go out into the circulation, they can actually kill the penicillin or cut the penicillin before it will reach into the wall. That's how smart this bacteria, right? All right. So I'm just giving you guys an idea. So that's something that I want you to pay attention, that beta lactamases. If you have those resistant, that means they've already been cutting them. Your bacteria already released that beta lactamases. But there's a lot of study out there that they really look into like how this bacteria behaves, so they were able to actually develop more antibiotics. Okay, so what did I just mention? The difference between gram-positive cocci has a thicker peptidoglycan, meaning any antibiotics can just go in there and go to that protein binding, penicillin protein binding, and then kill it, right? So, in other words, it's really easy to kill gram-positive cocci versus the gram-negative cocci. So why? Because the gram-negative cocci, they have the outer membrane. The concentration of beta-lactamases is within that parameter, right? So before you get into the inside of the cell of the bacteria, where your penicillin binding protein, let's just say this is your penicillin binding protein on this area here with those number one, it has small porins, very tiny. Not all big antibiotics can penetrate that, so there's a really what we call the super smart antibiotics or penicillin to get there. However, with the beta lactamase, they're all in that area, and there's a lot of them that just cut the penicillin if you're giving them the penicillin, or if you're giving them cephalosporin, they're just cutting it. Okay, so that is why the gram negative cocci is hard to kill because of that concept. Okay, again, this is your gram positive bacteria cell wall. As I've mentioned, look at your peptidoglycan cell wall versus your gram-negative bacteria cell wall. Okay, so as a nurse, I want you to understand that. Not just say, well, it's gram-negative cocci, but yeah, what is the composition of the two, right? So if you understand now, thank you. Please don't throw that information away. It gives you the idea when you're doing your multidisciplinary rounding. Why are they talking about gram-negative cocci or gram-positive cocci and what antibiotics? So I think my next class will be the different antibiotics that will kill either gram-positive cocci or gram-negative cocci. Okay. But I think this is just an introduction to what is bacterial wall synthesis. How does bacteria form their cell wall? Because it's really important that we understand that. Okay, why? Well, now look at this. How are we going to destroy? Remember I told you about the formation of your amino acid? You want to kill that, right? You want to destroy that. You want to stop that from happening. What medication are we giving? Well, I learned from my, at the bedside many years ago, you give them cycloserine. So cycloserine are the medications, cyclosporin, something like that. Um, you Google it, whatever the cycloserine medication that you guys are using, that's what they are ordering, on top of the other medication. So we're gonna go all of the medication that you guys are giving in the ICU. Okay, if your patient is having gram-positive cocci or gram-negative cocci, so you want to kill those. You want to prevent from forming more cell walls, bacterial cell walls. Okay, you want to stop bactophenol phosphate, right? You want to stop him from transporting this NAMNAG outside the membrane. So, what medications are you giving? They're giving them basic tracing. Although we don't push basic tracing because it's very toxic. We give it topical, right? Because you go to Walgreens or pharmacy and you buy them there like basic tracing ointment. When you think like, oh, I cut my nail, you have a splinter, or you have cuts, and now it's starting to red and pus, and so that's what you try to prevent, right? You treat it with your basic tracing ointment, and what you do there is you're stopping that bacterphenol phosphate from moving this um, simple sugar out of the system to form a cell wall. Okay, basic tracing. So cycloserine, basic tracing, they act on the different side of the cytoplasmic membrane. Another enzyme that we try to kill is the process of glycosylation, right? You want to stop them from binding together. So, what medication you gonna stop that from happening? Vanco, see, you want to stop that from forming together, right? Sticking together. Vancomycin. So when you're giving them vancomycin, what you're trying to do is to prevent glycosylation so that they're not gonna stick together, right? So that is why the doctors is ordering vancomycin so that to control the growth of your bacteria, the proliferation of your bacteria, right? So it stop. So give them vancomycin, it won't grow any more bacteria because you are stopping that glycosylation. And then you want to stop the transpeptidation, right? Transpeptidation, the cross-linking of the peptides. So when you do that, they won't attach their nose together. They won't form a web. And what medication do we give? You will give all your beta-lactam antibiotics, which are your imipenem, right? Things like that. So I'm hoping that you guys understand. Again, cycloserine, it stops the triggering of amino acids or protein synthesis inside the membrane to create peptide, right? And basic tracing is you want to stop the BPP from that transporter from transporting the NAMINAG outside the cytoplasmic membrane. And you want to stop the glycosylation from using vancomycin. You want to stop transpeptidation with your beta-lactam antibiotics. Okay? So, review here. So, with this, you want to stop the transpeptide cross-linking. What medication again that we said? The beta-lactam antibiotics. Good. And here, you want to stop from forming the amino acids, right? Like the L-alanine, glutamine, lysine. So this is your cycloserine medication. And here, you want to prevent from the glycosylation process. You want to give them the vancomycin, right? So vancomycin, the beta-lactam antibiotics, your your basic tracing from your BPP, and here is your cycloserine. Okay, Bacterial wall have a long glycan unit, just one unit. It's just form like a very long peptide chain, and that is what we call peptidoglycan. So peptidoglycan is the shape, right? Remember, penicillin and cephalosporin are very vital for microbes, right? So P for penicillin, C for cephalosporin, A is for your aminoglycoside, V is for your vancomycin, C for your Cipro, and then F for your fluoroconazole and metronidazole for your M. So I'm hoping that you guys understood something in here, so that you have a better understanding how bacteria form or synthesis. Thank you so much, and I think that's the end of my presentation. Bye.